Source follower. Our analysis of the common source stage indicates that to achieve a high voltage gain with limited supply voltage, the load impedance must be as large as possible. If such a stage is to drive a low impedance load, then a buffer must be placed after the amplifier so as to drive the load with negligible loss of the signal level. The source follower, also called the common drain stage, can operate as a voltage buffer. Illustrated in figure A, the source follower senses the signal at the gate and drives the load at the source, allowing the source potential to follow the gate voltage. Beginning with the large signal behavior, we note that for V in less than VTH, M1 is off and V out is equals to 0. Here you can see the figure A, source follower, and B, its input output characteristic. As V in exceeds VTH, M1 turns on in saturation for typical values of VDD, and ID1 follows through RS. Figure B, as V in increases further, V out follows the input with a difference level shift equal to VGS. We can express the input output characteristics as 1 by 2 nu and C naught x W by L V in minus VTH minus V out square RS is equal to V out. Let us calculate the small signal gain of the circuit by differentiating both sides of equation with respect to V in 1 by 2 nu and C naught x W by L 2 into V in minus VTH minus V out into 1 minus dou VTH by dou V in minus dou V out by dou V in into RS equal to dou V out by dou V in. Since dou VTH by dou V in equal to neta dou V out by dou V in, dou V out by dou V in equal to nu and C naught x W by L V in minus VTH minus V out into RS by 1 plus nu and C naught x W by L V in minus VTH minus V out into RS into 1 plus neta. Also note that GM equal to nu and C naught x W by L V in minus VTH minus V out. Subsequently, AV equal to GMRS plus GMRS by 1 plus GM plus GMB into RS. The same result is more easily obtained with the aid of a small signal equivalent circuit. From figure, we have V in minus V1 is equal to V out. V in minus V1 is equals to V out. VBS equals to minus V out, and GMV1 is minus GMB. V out is equals to V out by RS. Here you can see the figure, small signal equivalent circuit of source follower. Here you can see the figure, voltage gain of source follower versus input voltage. Thus V out by V in equal to minus is equals to GM RS by 1 plus GM plus GMB RS. Sketched in figure versus V in, the voltage gain begins from 0 for V in similar to VTH, that is GM is similar to 0, and monotonically increases as the drain current and GM increase. AV approaches GM by GM plus GMB is equals to 1 by 1 plus neta, since neta itself slowly decreases with V out. AV would eventually become equal to unity, but for typical allowable source bulk voltages, neta remains greater than roughly 0.2. An important result of equation is that even if RS similar to infinity, the voltage gain of a source follower is not equal to 1. We return to this point later. Note that M1 in figure does not enter the triode region if Vn remains below VDD. In the source follower of figure, the drain current of M1 heavily depends on the input DC level. For example, if Vin changes from 1.5 volts to 2 volts, ID may increase by a factor of 2 and hence VGS minus VTH by root 2, thereby introducing substantial nonlinearity in the input-output characteristic. To alleviate this issue, the resistance can be replaced by a current source shown in figure A. The current source itself is implemented as a NMOS transistor operating in the saturation region, figure B. Here you can see the figure source follower using an NMOS transistor as current source. To gain a better understanding of source followers, let us calculate the small signal output resistance of the circuit in figure A using the equivalent circuit of figure B, and nothing that V1 is equals to minus Vx. We write Ix equals to minus Gm Vx minus Gmb Vx equals 0. Here you can see the figure calculation of output impedance of a source follower. Here you can see it follows that R out equal to 1 by Gm plus Gmb. Interestingly, body effect decreases the output resistance of source followers. To understand why, suppose in figure C Vx decreases by delta V so that the drain current increases with no body effect. Only the gate source voltage of M1 would increase by delta V with body effect. On the other hand, the threshold voltage of the device increases as well. Thus, in VGS minus VTH whole square, the first term increases, the second order and the second order decreases, resulting in a greater change in the drain current and hence a lower output impedance. The above phenomenon can be studied with the aid of the small signal model shown in figure A. It is important to note that the magnitude of the current source GMB VBS is, here you can see the figure, source follower including body effect, linearly proportional to the voltage across it. Such behavior is that of a simple resistor equal to 1 by GMB, yielding the small signal model shown in figure B. The equivalent resistor simply appears in parallel with the output, thereby lowering the overall output resistance. The reader can show that output without 1 by GMB, the output resistance equals to 1 by GM, concluding that R out is equals to 1 by GM LL to 1 by GMB is equals to 1 by GM plus GMB. Modeling the effect of GMB by a resistor which is only valid for the source follower also helps explain less than unity voltage gain implied by equation for RS similar to infinity as shown in figure. Representation of intrinsic source follower by a Thevenin equivalent. The Thevenin equivalent of figure AV equals to 1 by GMB by 1 by GM plus 1 by GMB equal GM by GM plus GMB. For completeness, we also study the source follows of figure A with finite channel length modulation in M1 and M2. From equivalent circuit in figure B, we have AV equals to 1 by GMB parallel to R01 parallel to R02, RL by 1 by GMB parallel to R01 parallel R02, RL plus 1 by GM. Here you can see the figure A, source follower driving having low resistance, B, small signal equivalent circuit. Source followers exhibit high input impedance and a moderate output impedance, but at the cost of two drawbacks: non-linearity and voltage headroom limitation. We consider these issues in detail as mentioned in relation to figure A. Even if source follower is biased by an ideal current source, its input-output characteristic displays some nonlinearity due to the nonlinear dependence of VTH upon the source potential. In submicron technologies, R0 of the resistor also changes substantially with VDS, thus introducing additional variation in the small signal gain of the circuit chapter. For this reason, typical source followers suffer from several percentage of nonlinearity. The nonlinearity due to body effect can be eliminated if the bulk is tied to the source. This is usually possible only for PFTs because all NFTs share the same substrate. Figure shows PMOS source follower employing two separate N wells so as to eliminate the body effect of M1. The lower mobility of PFTs, however, yields a higher output impedance in this case than the available that available in an NMOS counterpart. Source followers also shift the DC level of the signal by VGS, thereby consuming voltage headroom and limiting the voltage swings. To understand this point, consider the example illustrated in figure: a cascade of common source stage and a source follower. Without the source follower, the minimum allowable value of Vx would be equal to VGS1 minus VTH1 for M1 to remain in saturation with the source follower. On the other hand, Vx must be greater than VGS2 plus VGS3 minus VTH3 so that M3 is saturated. For comparable overdrive voltages in M1 and M3, this means the allowable swing at Vs is reduced by VGS to a substantial amount. It is also instructive to compare the gain of source followers and common source stages when the load impedance is relatively low. A practical example of the need to drive an external 50 ohm termination in a high frequency setup as shown in figure A. The load can here you can see the figure PMOS source follower with no body effect. Here you can see the figure cascade of source follower and CS stage. Be driven by a source follower with an overall voltage gain of V out by V in SF similar to RL by RL plus 1 by GM1. On the other hand, as depicted in figure B, the load can be included as part of common. Here you can see the figure A, source follower, B, CS stage driving load resistance. Source stage providing a gain of V out by V in CS similar to minus GM1 RL. Thus the key difference between these two topologies is the achievable voltage gain for a given bias current. For example, if 1 by GM1 similar to RL, then the source follower exhibits a gain of at most 0.5, whereas the common source stage provides a gain close to unity. Thus, source followers are not necessarily efficient drivers. The drawbacks of source followers, namely nonlinearity due to body effect, voltage headroom consumption due to level shift, and poor driving capability, limit the use of this topology. Perhaps the most common application of source followers is in performing voltage level shift. As explained in chapter, source followers also induce substantial noise. For this reason, circuit of figure B is ill suited to low noise applications. Thank you.